All right, welcome back, everybody. Yeah, this is the third part of this lecture set, and I actually started recording this lecture a week ago, and it was my computer died in the middle of it. I don't know why; it still hasn't been fixed, but I got a new one. Everything's now set up. It took a while to get back on my feet again, my digital feet, I guess. So we're just going to walk through the rest of this, and the topic of the final set, our lecture in this set, is t-tests. And we kind of already know basically everything we need to know about the mechanics of t-tests, except for what a t-distribution is. So I'm going to walk you through another example hypothesis test by the time we get to the end of this lecture. But before we do, we should talk about why we're running t-tests and not z-tests, which I've been putting in quotes pretty faithfully throughout this entire lecture. So hopefully you haven't gotten the impression that z-tests are something we actually do, because we don't. Instead, we use t-tests. And the problem with potentially using z-tests is the fact that we don't know what the population standard deviation is. We just assume that it's the same as the standard deviation of the sample. And actually, this is an error. The error is that I shouldn't be using standard error. I should be using standard deviation, I think. Yeah. Yeah, it's the standard error that we calculate on the basis of the standard deviation of the sample. So based on that assumption, we just go from standard deviation of the sample and say, well, that will tell us what the population standard deviation is, and then we can calculate the standard error, which is the standard deviation of the sampling distribution using that equation that we learned. Then we can, calculate these z-scores for the sample means that we get out of these tests that we run. So I'm sorry for the terminological confusion, but I think it's pretty obvious based on what I just said why there can be a fair amount of confusion when we're talking about these sorts of things. I'm not going to go through the mechanics of that again, although we'll touch upon it as we go. But basically, we're making that leap from the sample standard deviation to the population standard deviation without actually knowing for sure that it's a valid thing to do. So because we're making that assumption, we wind up with what is technically called a t-score if we're doing this the right way. And that's the only time I'm going to put t-score in brackets there or quotes there rather than a z-score. So the t-score will fall on a slightly different distribution, which we're going to call a t-distribution. And that is to say it's not a normal distribution, but the two do look fairly similar to each other. So let's compare, shall we? So I'm going to walk you through a couple of R commands that you can use to look at the difference between the two. And maybe, I'm sorry, again, I just set this up. And so the font is not that big in R, but we can make it bigger, hopefully big enough for you to see it. So I'm going to copy that command, and we've seen this one before. So this is what the command spits out when I actually run it in R, and it's a normal distribution. If we take a look at the specifics of how this distribution was created, we can see some old friends here, hopefully, that look familiar. So we're using this dnorm command, which gives us a normal distribution. And the mean of that normal distribution is 0, and the standard deviation is 1. So this is that standard normal distribution that I talked to you about. And it ranges from -5 to 5. So basically what's being plotted here on the x-axis is z-scores. So yeah, and this will come up later, so I'll just remind you that within one z-score of the mean, we should expect to get about 68% of the distribution. Within two standard deviations or two z-scores of the mean, we should be able to get 95% of the distribution. So on the tails here, beyond -2 and beyond 2, we're only getting 5% total or 2.5% on either side, right? Okay, so that's a normal distribution. That's what it looks like. And in particular, it's the standard normal distribution. We'll compare that to the t-distribution, and we'll plot this one in green. So before I show you what it looks like, I'll just kind of highlight the differences between these two commands. So on this one, we have, instead of dnorm, we have dt. So this is just distribution t, I guess you could say. And we're going to do some other things here. I'm going to add a main label to it, a title. And I'm also going to add equals t to say that we're adding this one to the original normal distribution plot. And then we're also going to color the t distribution green. Other than that, the interesting differences lie mainly in here, which is that for the t distribution, we don't specify a mean and a standard deviation. Instead, we specify df, which stands for degrees of freedom. And the degrees of freedom in this particular case will be 3 only. And we'll change that as we go so we can see what effect that has. Otherwise, we're going to plot it on the same range with basically the same y-axis range as well. So what does it look like when we do that? We get this green creature here, which hopefully you can see okay. I'll move this over here because I often put my face on the right-hand side of the screen when I make these videos. But yeah, it looks kind of like the same shape, but it's not quite exactly overlaid on top of this normal distribution, right? So it's a little bit shorter here in the middle. I don't know why that keeps happening, sorry. It looks a little bit shorter here in the middle, and then it looks a little bit higher here in the tails. And we can maybe compare that to the next command I was going to run. So I'm going to add this next t-distribution in blue right here. And the degrees of freedom of this guy are going to be 6, so a little bit higher in that variable. What happens when I do that? Well, I get something that's kind of in between the normal distribution and the first t-distribution that we created. So this blue distribution is kind of halfway in between the two here, so it's a little bit higher in the middle than the green one is, and it's a little bit shorter, I guess you could say, here on the tails, or flatter maybe if you prefer to think of it that way. So yeah, it's kind of squeezing in the middle there. There's kind of a transition point here, I guess. But the point is that neither of those is going to look exactly normal. It's kind of funny if I go back to that original, the green one with 3 degrees of freedom, and just plot it by itself. You might look at this and say, oh, that's a normal distribution. If you're just kind of not that concerned about the specific details, it kind of has that general shape, right? It's not exactly the same shape as that normal distribution though, right? Because of the reasons we just mentioned. It's fatter here in the tails. But if I add this blue one to it, it'll look, fairly similar. And maybe if I plot the blue one by itself, it'll look a little bit more normal to you. Yeah, and in fact, if I keep cranking up these degrees of freedom, let's go up to 26. It'll start to look more and more normal, it turns out. It's going to flatten out here in the tails, and it's going to get higher in the middle. Everything's going to get kind of squished into that normal pattern. We'll go 1 to 26. Yeah, it's doing the same thing, squeezing more towards the middle than what we saw before. So the degrees of freedom change the shape of the t-distribution. The more degrees of freedom you get, the more normal it's going to look, or the closer it will look like to a normal distribution. So normally I ask that question in class, but I can't ask it in live on this video because it's not live. So I'm just going to answer it for you as I go through, but that's what's going on here. So this kind of summarizes what we just saw. Normal and t-distributions look very similar, but the t-distribution flattens out at the top and expands on the sides with fewer degrees of freedom. So since we've seen that shape, and we can see it again here in this graphic that I copied over from R, the first question to think about is what effect would using a t-distribution have on our interpretation of the results of a hypothesis test? So we were looking at that in the last lecture in this set, and kind of the way I wanted you to think about it, hopefully, which was helpful. Did I pass by it? Yeah. Is to think about like where does our sample mean fall on like the sampling distribution, right? So if our sample mean is way out here in the tails, then it's not likely to have arisen from a population which has a mean around here, like not close to that tail. So if we go back here and think about that, just to kind of go back to that basic fact I told you before. So let's say we have a z-score from our z-test of -2. That's going to put me out here where there's only 2.5% of the normal distribution to the left of it. And there's also, if I had a z-score of 2, there'd be 2.5% higher than that. But basically what I wind up with, if I just look at one side of the distribution, is a z-score of -2 will give me a p-value of 0.025. That's less than our kind of conventional alpha criterion of 0.05. So in that case, we'd say, well, we have a significant result. We have this z-score of -2. It's far enough away from the hypothesized population mean of our distribution to say that it's not likely to arise just from chance. Sometimes it will, but more often than not, it will be the result of an underlying population with a different mean, somewhere closer to where we're getting the sample mean from, basically. That's how we'd interpret a z-test if we were to run it. But if we got instead of a z-score of -2, we've got a t-score of -2, and we're on, say, this green distribution. Let's say we had a degrees of freedom of just 3. Then all of a sudden, here, I'm kind of higher up in the overall distribution shape, but kind of more importantly, there is more of the distribution over here underneath this part of the curve than there is for the normal curve, for the black one at the bottom. And that means my p-value is going to be higher if I'm even if I'm at the exact same spot in sort of the x-axis scale. I'm going to get a higher p-value for the t-test than I will for the z-test. And I don't know if it's at t equals -2, I'm exactly going to be over that kind of crucial value of p of 0.05 or not. But I'll be closer to it for sure than I will for the normal distribution. And if we keep kind of creeping over here closer and closer to 0, at some point I'm going to get a t-score value which will be interpreted as not significant, when a z-score of the same value would be interpreted as a significant result. Basically what I'm trying to say here is that the t distribution or the t-test is going to be a more conservative test. It will give you less significant results, or I guess fewer significant results, based on the mathematics involved, because there's simply more of the distribution over here to the left of the t-score than there is for the normal distribution. So even for the same sort of t-score, z-score equivocation, I guess you could say, you're going to get higher p-values for the t-test than you will for the z-test. So you will get less or fewer significant results, and presumably for the same reason, you're going to get fewer false alarms out of that t-test than you would for the z-test. The other question we should think about here is what effect would increasing n have? And I'm going to change this a little bit. Actually, maybe I won't. So n here is that the number of observations in your sample. And we haven't talked about degrees of freedom, and maybe I should walk you through what I want to say about that before I come back and answer this question. But it's tied to sort of this combination of t-distributions and normal distribution that we can shapes that we can see here in this graph. So basically, the main takeaway from this point is that the t-test is going to be a bit more conservative than the z-test, and it will give you hopefully fewer false alarms or type 1 errors for that reason. And then we also want to think about what would it change if we changed n, or the number of observations in a sample. And one guy who could tell you all about this is statistics all-star #1, a guy named William Gossett from back in the old days. He developed the t-test while he was working at the Guinness Brewing Company, like the same Guinness Brewing Company that's still around that makes Guinness beer. They're from Ireland, as you may very well know. And he was trying to figure out, how to make the best beer possible. And I'm sorry, this little detail is going to bother me. But he was trying to deal with the problem of evaluating the quality of the small samples of beer ingredients they would get from various suppliers. So I guess the suppliers didn't want to give them a huge stack of whatever. And instead of that, they would give them just small samples, and he'd try to figure out, well, which one of these is better than the other. And he found that sort of like the z-test approach that I guess maybe was in existence at the time wasn't really suitable for this, because basically what winds up happening is the degrees of freedom are too small for small samples, right? So he figured out a way to do this, and it's the t-test approach to doing it using a t-distribution rather than a normal distribution. And kind of the funny, I guess, human side of this story is that he published his approach under the name of student, in quotes, because the Guinness Brewing Company forbade their employees from publishing anything. Apparently a previous employee had published some of their trade secrets, and they didn't want to get any more of their trade secrets out there because they had to have like a special corner in the market, right? So they didn't know what he was up to exactly in terms of publishing it. And, it's kind of funny to think about that he didn't really have to publish it in any way, right? He could have been just, I guess, capitalistic about it and just said, hey, Guinness, now we have this sort of like analytical advantage at our disposal that no other brewing company has. But he put it out there. And then for that reason, it's the test itself has forever been known as student's t-test. So you might hear that term thrown around. And he wasn't a student at the time. He was an employee, right? It's not employee's t-test. That would have given the game away. But yeah, that's what he's known for and why. And one of the other things he did is that he shared his knowledge as well. So he sent the tables for t-distributions to his statistical mentor, a guy named Ronald Fisher, who I've mentioned before, stating, I'm sending you a copy of students' tables as you are the only man that's ever likely to use them. And guess what? That's not true. Sometimes we have big ambitions for our research results and think, oh, this will change the world and everything. And then like maybe one person cares. Student, Mr. Gossett, thought that maybe one person would care, and it turned out that the whole world cared because many people have used this t-test approach ever since, right? It's common in statistical analysis. So good on you, William Gossett. I can tell you a little bit about his mentor, and as I read through this, I'll say that the idea that Ronald Fisher was his mentor, I actually kind of probably should go verify all that, because when I was looking at the dates here, I wasn't sure how it all lined up. But Ronald Fisher was born in 1890, and he lived until 1962. But if he was born in 1890, then when William Gossett was doing this research in 1908, Ronald Fisher would have been 18 years old. And so I don't think he was mentoring him at the time. So maybe this is a relationship that developed later. Again, sorry, I'm not a real statistician. I don't know all the ins and outs of the history of the field. But I do know that Ronald Fisher was a very influential part of the field, kind of almost like Chomsky-like figure in the history of the development of statistics. I don't want to go too far with that analogy, but he's one of the important figures in the early development of stats in the 20th century. And he developed a lot of different tests that we still use to this day as well, including one called analysis of variance, or ANOVA, which we'll talk about in this class. We'll also talk about F distributions and F tests that kind of feed into ANOVA as well. Also, a technique known as maximum likelihood estimation, which is kind of cool, but we don't have a lot of time for in this course. But he had lots and lots of different ideas, and the one that we want to focus on for the moment is the idea of degrees of freedom, which he developed as well. And he kind of he was the right, I guess, missionary for this testing approach, because as soon as the idea got into his head, he spread it around through his world of influence. And one of the reasons why is because degrees of freedom kind of tied into his, t-test used that degrees of freedom concept. So I guess it wasn't totally selfless on his part. He was trying to sort of, evangelize his own vision of how stats should work as well in promoting William Gossett's work too. I guess I will say, as long as we're here, and this is the part where my computer died last time, so I don't even know if I should say this. Maybe it was the ghost of Ronald Fisher trying to kill off my message. But sorry, there's something on my glasses. The Ronald Fisher has kind of fallen out of favor, or as like sort of like I don't know how much there's like Ronald Fisher worship or something like that. There's to some extent kind of Noam Chomsky worship in the world, I think, as as a linguist, or maybe somebody who likes politics. But Ronald Fisher was one of those sort of like really strong personalities, I guess, and also was kind of part of the thick of like the intellectual climate back in the early 20th century, which is a time when, for whatever reason, a lot of intellectuals got on board with the idea of eugenics, which is the idea that, certain genetic traits or certain groups of people perhaps are, better or than others. And we should try to be sort of like funneling humanity towards like the better traits rather than the worse traits, which is an idea that is generally looked at as gross nowadays and certainly disfavored. And so partially for that reason, Ronald Fisher is no longer looked upon as such a great guy. And again, I don't know to what extent he was before, but there's also another movement afoot in stats that is moving away from Ronald Fisher's approach, this sort of null hypothesis significance testing approach, and instead moving to what's called more of a Bayesian approach, where instead of saying, you run a test, you get some sample statistics from that test, and then you make a decision about what it says about the underlying reality, which you can't know absolutely for sure. And instead of making that sort of interpretive decision about what's going on. In Bayesian analysis, you sort of, have a pre-existing set of notions called priors based on hopefully reason and evidence. And then you run a test and get some more data about that hypothesis. And then you just kind of update your hypothesis. You don't reach it like a final conclusion, but you say, well, based on what I know now, I'm going to shift my priors to like this new position, which is hopefully more accurate, but I don't like have a final statement to say about it. I can't remember if sorry, so much is going on, but I can't remember if I've talked to you about sort of the replication crisis in stats. I think I was in the middle of that in the previous lecture, and if I've said this before, I apologize, but it's in the randomness link. And in fact, in case I have, I'm not going to say much more about this, but there's a link there about science's significant stats problem, which is kind of about that, where people have like looked at results from previous research and found that oftentimes they can't replicate the same significant effects that they got before. And so I'm just going to say this, and if I find that I've said it before, I'll just edit it out, I guess. But there's a general principle in scientific research or social science research in particular that you can only really publish a significant result, because if you don't get a significant result, you've kind of just run a bunch of, you've run an experiment, collected a bunch of data, but not shown anything new or different about the world than we either assumed or knew already. So what's the point of reading what you did? That's kind of the mindset that I was trained in for sure. But so one of the problems with that is there's a lot of pressure to only publish significant results, which kind of makes sense, but then it also puts a lot of pressure on the scientists to get that sort of p-value to be less than 0.05 so that they have something to say. And maybe 0.05 is not the right value to set for alpha, it turns out, because you could get a fair number of, 1 out of 20 spurious results that way, and 1 out of 20 false alarms in terms of what we think is significant or not. And people, as they've kind of in the recent last decade or so, have learned that, a lot of these results that were published as significant before are hard to replicate, or maybe just don't replicate at all. I know in linguistics, there's not much work done on replicating previous findings, right? Everybody's kind of like in their own pigeonhole and doing sort of their own thing because, that's just the way linguist minds work. And that's also kind of the way research works as well. We got to find our own little niche and corner to kind of do something new and different again. So people aren't kind of going back all that often to previous research and trying to replicate the same result. For instance, I'll give you a personal story. My own dissertation research was about, whether place assimilation patterns are more based on, say, production factors like ease of articulation factors versus perceptual factors like ease of discrimination or what have you. And I got some evidence that they cross-linguistically, place assimilations probably due more to articulatory factors. But that was primarily based on 1p value of like 0.04 or something. And since I had collected all the data and analyzed it, I was like, I don't know how much I trust myself. Like, it was kind of a cool like combination of results, but I never published it. But either way, it took a ton of work to get there. It took me like a year and a half to do that dissertation. And it's very unlikely that somebody would be so interested in that particular little niche topic or the specific way I approached it to replicate that all again. Like, people are interested in like ease of articulation versus ease of perception in terms of like explaining phonetic patterns for sure. So I probably should publish it and just let the world decide. But again, do what I say and not what I do. Either way, it's not probably ever going to be replicated. What I did, it will probably not ever be replicated again. Like, I was literally like, processing data for months, and I don't think most people want to do that. So there's some knowledge that was gained there, but it's not necessarily clear if it's how solid that knowledge is. And that applies not only to my research, but to everybody else's. And as people are starting to kind of think about these statistical techniques we use or assume have to be the ones we do use, they're finding that maybe there are some inherent flaws with that. So you can read this article. That it's written for a more general audience, and you can find out more about that if you want. But this is a general issue throughout all of science. And one of the sort of implications for this is that people are kind of moving on to a little bit to, maybe it's okay to publish research or talk about research that doesn't get significant results. Yeah, I don't know how much the overall climate with that has changed, though. So for now, we're going to still focus on how do you get those significant results and how do you interpret them once you do. And we can, again, thank Ronald Fisher for a lot of this, or also blame him for a lot of this. Conservation of everything. It's hard to be all good or all bad. So I kind of already talked about that, but I want to go back to this idea of degrees of freedom, which we've talked about before. It means it's the number of values in the final calculation of a statistic that are free to vary. Sorry, I'm slurring my words today. A bit jet-lagged, I guess. Anyways, we talked about this when we learned how to calculate variance, where variance was equal to the sum of squares or square differences in a sample data set divided by the degrees of freedom. And in that case, degrees of freedom was equal to n minus 1. So n is the number of observations in a sample, and you subtract 1 from that. The reason you subtract 1 is because you calculate a statistic from those sample observations, namely the mean of those observations, and then that's no longer free to vary when you calculate the sum of squares, so on and so forth. I'm not going to go through all that again, but just in case you needed a reminder, that's kind of what we're talking about. I also have a reminder that standard deviation is the square root of this quantity. But either way, we're going to use the same kind of concept of degrees of freedom when calculating t-statistics, so t-scores when we do t-tests, and that's part of the reason why Ronald Fisher liked this sort of approach. So yeah, let's try another null hypothesis significance test. We're going to do it slightly differently than the one we did before, though. So we're going to test the possibility that the mean of the VOT of the unaspirated stops in our little data set is greater than 0. So this is not an unreasonable hypothesis to have, that if a stop is unaspirated, it shouldn't have any aspiration at all, which is a 0 millisecond VOT, right? Well, is that true in this particular case? So we can try looking at this in two different ways, which will basically be the same approach, but they'll look different when we apply them in R. But I'm going to get you started by first creating the unaspirated data set here from our VOT data. So I'm just filtering out just the unaspirated stops, and we're going to run a so-called z-test the hard way in R. So again, just as a reminder, I'm calculating the standard error with what's on the bottom of my fraction here. So this is the standard deviation of my sample set VOT divided by the square root of n, the number of items in that data set. And then in the numerator of my fraction, I've got 0, which is my hypothesized mean VOT from my population, and I'm subtracting the sample mean from that. And we're doing this in a different order here than we did before. I'll explain that in a second, but I'm going to hit return. And I'm creating a ratio here. I'm calculating the value of a fraction, and then I'm going to feed that into this p-norm value to let me know. So this basically gives me a z-score, and then I convert that z-score into a probability, which I can interpret based on the rules of our null hypothesis significance testing paradigm. And that p-score is 0.119, so on and so forth. Okay, so that's higher than 0.05, which is kind of the crucial part of that. I wanted to highlight this bit here before I talk about the interpretation of that. But the numerator, I reversed the order of the terms. So before we had the mean minus the hypothesis. So before we had the sample mean, and then we subtracted the hypothesized population mean from that. Here I'm doing that in the exact opposite order, and I get negative 4.66. So that means that the sample mean of unaspirated VOT in my data set is negative 4.66 milliseconds. All right, so that's not super far away from 0, right? If I were to do it in the opposite order, I'd get positive 4.66, right? It's not that controversial. But the reason I'm doing it in this order is because what I'm looking at is whether or not the proportion of the normal distribution is greater than that sample mean. So before we looked at the sort of less option. In this case, we're going to look at the greater than option. So yeah, I'll show you how to do that here briefly in R using just the t-test command. Then I'll kind of talk about it a little bit with respect to what this looks like in terms of those distribution shapes. But the kind of crucial part here is I'm just going to run a t-test using my unaspirated VOT scores. And then my hypothesized population mean is just 0. And then I'm going to consider the possibility that the actual observed VOT is greater than this hypothesized mean VOT. And this should spit out more or less the same p-value, but like I said, it's a little bit more conservative. So the sort of z-test value I get is 0.119. And when I run this as a t-test, I get 0.1201, which is slightly higher than the z-test score. Yeah, but otherwise the mean is the same, right? So it's 4.66. And if I go back to these distribution shapes, you'll see different scores here on the x-axis, right? So I'm hypothesizing that the mean is 0 rather than 100. But what I'm looking at is how much of the distribution is higher than my sample mean when I test the greater than hypothesis. So I apologize that I didn't come up with the exact analogous graph for this, but basically you can imagine I'm like in this graph would be like 104.6 something, and then I've got 12% of my distribution shape to the right of that. That's the amount of the distribution that is greater than my sample mean. Rather than before, we were looking at how much is less than that sample mean for the aspirated stop case. It kind of winds up looking the same. You just kind of have to flip your mind to think about, which part of the tail or which tail I'm looking at or which part of the distribution I'm looking at. But to kind of give you the punchline for this, number one, I've answered this question before, which one has the higher p-value? It's the t-test. Both of them, though, give us roughly the same probability, which is a p of 0.12. So how do we interpret that result? And we interpret it as not a significant effect. So this is one of these null effects that I was mentioning before in talking about the replication crisis in social science. But on the basis of that result, we would say we'd accept the null hypothesis that the mean VOT of the unaspirated stops is 0 milliseconds. So we just put it out there like, what if, the mean VOT of unaspirated stops is 0 milliseconds? We have good reason to think that that might be the case. Let's collect some data from unaspirated stops and see what their mean VOT is. We get an actual value of like 4.6. And it turns out that's not different enough from our hypothesis for us to reject that hypothesis. So we accept it. We start out with that as our default assumption, and we keep that default assumption because we don't have reason enough to say it's not the case. Since we've just assumed that value, that underlying mean value of 0 milliseconds VOT for these stops, we can't really prove that that is actually the mean value for those stops. We're just going to go on and keep assuming that's the case until we're proven wrong, basically. So yeah, that's kind of another issue with this, is that you can't really prove anything, right? We're always making a guess at some level. And so underlyingly, we've got a guess as sort of creating the foundation of our understanding of this situation. And we're just sticking with that guess because it doesn't seem to be inconsistent with the data in any serious way. That's how we interpret that result. And if that didn't make sense, you might want to walk through that loop of the video again. Basically, we're saying this is not a significant result, and we're not going to change any of our underlying assumptions. I wanted to go back to that other point, though, that I was starting to get to about like which tail of the distribution we're looking at. So we could run the test a different way and say, is the mean VOT of the unaspirated stops less than 0 milliseconds? And in that case, what p-value would you predict for that test? And to kind of help you understand how to answer that question, because again, I'm not asking it live in class, we can go back to this distribution, which we used as our example for the first hypothesis test we ran. And so before, when we're testing the less than hypothesis, we were looking at how much of the distribution is over here on the left tail of the distribution. Here, we're looking at the greater than hypothesis. So we're getting a sample mean around here. And then we're saying, well, we had 12% of the distribution to the right of that sample mean point. We had 12% of the distribution that was greater than that point. How much of the distribution is left to the left of that sample mean point? If I've got 12% over here, how much is over here on the left? It's whatever 100 minus 12% is. It should be about 88%. So if I run that test with the less than option, I should get a p-value of about 0.88. And lo and behold, that's exactly what I get. I simplified this to 12. It's 0.1201. So 0.1201 and 0.8799 add up to 1. That's the whole distribution. Yeah. And it's a little funny. I'll just mention this as a language geek, but it's funny that this option in R is known as greater than, and this one is just less. So greater than or less than, that's sort of the idea. So this is not lesser, it's less. And this is greater, not great. All right. I will try to stop making bad jokes. I can't promise anything. I'm a dad now. I'm contractually required to make them. But be that as it may, we can all survive because actually there's a third way to do this. And I think I'll talk about that and then I'll go back to that other question that I haven't answered yet. So we can run a t-test the third way, which is say it's a two-sided test. And when you do that, you look at both sides of the distribution at the same time. So you may be looking at this and saying, well, why, I've got a VOT of 0 milliseconds. Like, why am I just testing like the greater than option, right? What if the thing I care about is not whether the mean VOT is greater than 0, but just like different than 0, i.e. not 0. It might be greater than, or it might be less than as well, right? So how can I test that? And the way we do it is by running one of these two-sided tests. And here you basically take the p-value for the sample mean and you double it. And that enables you to check both sides of the distribution at once. So this is a little bit funny, but I'll show you how it works using the data we've just been playing around with. So we're going to go back to that unaspirated VOT again. And our sort of null hypothesis is that the mean value of the population VOT is 0. And instead of greater or less than, we're going to say two-sided in this alternative parameter here in the t-test syntax. And what that's going to do is take this p-value right here, and it's going to double it. And it's going to give me a p-value of 0.2402. So it's going to basically take, the part of the distribution that's to the right of 4.66, and then if I were to flip it over on its side and say how much of the distribution is to the left of negative 4.66, that's another 12%. So it's 24% in total. And what that does is that it's going to make the test overall just much more conservative, right? So that is going to increase the p-value of the test in all cases, except I guess when it's 0, but you never really get that anyways. So it's going to be more conservative than a one-sided t-test. It's going to be much harder. It's going to be twice as hard, really, to get a significant result out of this approach. And there is generally a problem where we get too many significant results, in part because people just apply stats the wrong way sometimes, but also because we're motivated to get significant results. So we try to make them happen when we can. So for that reason, it's good when you're running the stats to try to be more conservative rather than less, right? And so one of the ways you can do that is by running these two-sided or two-tailed tests. So what determines the choice of whether you're using one of these one-sided tests versus a two-sided test is what you know about the problem before you run a test of statistical significance. But basically what I would recommend is that you should always default to that two-sided or two-tailed test, unless you have some specific reason to just expect the sample mean to be on one side of the distribution or the other. But it's always just good, principled stats to try to be more conservative rather than less, because you want to make the most convincing argument possible, right? If you come up with a significant result and it's kind of like hazy in terms of like how you got there, then less people or fewer people are going to be convinced. Less than people will be convinced. Stop talking. All right, so fewer people will be convinced by a weaker argument, so try to make the strongest argument possible. And one way to do that is to run sort of like these two-sided t-tests rather than a one-sided test. Also, just basic rules of thumb about how to apply this approach. You can choose your level of alpha before you run the t-test. And again, this is just, it's a parameter. You can set it to be whatever you want it to be. But like I said before, most people will just assume it's going to be 0.05. You can make your life a bit harder and say, I'm going to set alpha to be like 0.01 or 0.001 or something like that. And again, try to get a much stronger argument on the basis of that. But either way, you have to set that value before you run the test. You can't like pick and choose after the fact and say, well, I got a p-value of 0.06, so maybe I'll set my alpha to be 0.1 for that reason. It's like, no, you got to go into a blind and say, if I get a p-value less than this alpha value, then it's a significant result. If not, oh well, I got a null result, and probably nobody will want to publish it for that reason. But, we still might want to find out about what you did because, the methods can be valuable as well. And like I said, the world's changing a little bit on that score. But you have to run the game according to the rules, and this is one of the most important rules. Your level of alpha is determined before you run the t-test. I've got a couple of other notes here on a different kind of test called the paired samples test. But before I do that, I wanted to go back to this question that I hadn't answered yet, which is what effect would increasing n have on the interpretation of a t-test as compared to the interpretation of a z-test. And so what I pointed out here before is that the t-test is more conservative because these tails are fatter. But we also found out that with the greater degrees of freedom, then the t-distribution starts to look more and more like a normal distribution. And the way we can increase degrees of freedom in basically collecting a sample of data is by increasing n, by increasing the number of items in our sample. So remember, degrees of freedom is n minus 1. If n gets bigger, the degrees of freedom will get bigger as well. And the more our t-distribution for that data set will look like a normal distribution. So when you increase n, you're starting to create basically a less conservative test, but also presumably one that's more reliable because you're just collecting more data relevant to the situation, right? And also when you increase n, some of those assumptions about the central limit theorem start to be more valid, right? The idea that, this sample mean reflects the population mean in some meaningful way, so on and so forth, or that we can sort of intuit what the population standard deviation is from the sample standard deviation, so on and so forth. But overall, what this will do is it will start to make your t-distribution look more like a normal distribution. It's going to be a less conservative test for that reason. It's going to enable you to probably have a better chance of getting a significant result if there really is some sort of underlying significant result to be found in your data. That's what increasing n will do for you. The more data, basically I'll say it this way, you can cheat pretty much at any point in stats. And if you collect enough data on some topic, you can almost always get a significant result. But it depends on how significant that result is at the end of the day. I'll say more about that when we talk about power and effect size, so on and so forth. But increasing n basically increases those chances of getting something significant. And, you getting published and not perishing in the world of academia. Okay, so I'm not going to say anything further about that now, but that's the answer to that question. We've been through the rules of thumb. I need to talk a little bit about paired samples t-tests. These are pretty clever, and they're going to lead into our next topic, which is two-sample t-tests, but I'll talk about those in the next lecture set. What a paired samples test does is it expands on our t-test paradigm in a clever way to determine whether or not there is a significant difference between the observed values in two samples of data. So instead of just collecting one sample, we're getting two here, and then we're going to compare the two directly. So what we do is we convert the data into differences between paired samples from the two data sets. Couldn't see that coming from the name of the test or anything like that, but that's what we do. And what that gives you is a set of differences in a new data set. I'll explain this with sort of respect to the VOT data that we've seen here in our data set and also that you've collected now. But let's say, Amy has a VOT value for the P and Peel, and then Bobby has a different VOT value for the P and Peel as well. And then go all the way down the line of the word list that we read, like peel, pale, so on and so forth. Each speaker has read those words and gotten their own VOT values. If we want to compare like our Amy's VOT values different from Bobby's, we can just say, let's subtract Bobby's VOT values from Amy and look at the difference between the two, because otherwise they're exactly the same sort of data points. The only difference between them is one's Amy's and one's Bobby's. Otherwise, it's the same word, same stop, same vowel, so on and so forth. And then we get that set of differences in a new data set. And rather than worrying about two different samples of data, we just have one sample, which is the differences between the two. And so we can use a one sample t-test to determine whether that set of data has a mean that is significantly different from 0. Isn't that cool? So what we're going to do is we're going to say, well, if there's no difference based on like Amy versus Bobby in these two samples, then the mean of the differences should be 0. We might get a little bit of random noise or variation around that 0, but ultimately it's going to center around that, where sometimes Amy's VOTs are larger and sometimes Bobby's, so on and so forth. That's our null hypothesis, that there is no difference between the two. So we can test that directly using that approach that we just talked about, a minute or two ago. And I'll give you an example of how to do that. So let's look at the difference between the aspirated and unaspirated stops in our VOT data set. And this, we have reason to suspect they might be different, because otherwise, why would we call them two different terms? But I'm going to create this data set by just subtracting the one from the other. So we're going to start out with aspirated VOT, which normally is larger than unaspirated VOT, right? We've seen that before. I'm going to spit that into just a data frame or a vector called aspdiff. And then I will run a one sample t-test on that vector. And since I suspect that aspirated VOT will be larger than unaspirated VOT, I'm going to run it with the greater than option here. But it's only because I have that background reason to suspect that might be the case. The crucial part here is that I'm running this test with a hypothesized mean of the differences as 0. So I'm going to test whether the numbers in this vector are significantly different from 0 using this t-testing paradigm, kind of under the assumption that they're more likely to be greater than 0 than less than. And what do I get out of that? I get an extremely small p-value. So my t-score here is 19.394. The degrees of freedom is 209. The p-value is less than 2.2 times 10 to the negative 16th power. So that's like 16 zeros in a row, like 0.16 zeros and then a 2. It's much, much smaller than 0.05. So it's significant by a mile and then some. Well, the mean of my x, the mean of these differences is 89, right? So if remember, the aspirated mean was like 94, and then the unaspirated mean was like 4.6, whatever. So if you subtract one from the other, you get a mean value of 89.5. That's different from 0 by a lot if the degrees of freedom is 209. But if I do the same test using R syntax, I can simplify my life a little bit. So in this case, I'm going to look at the aspirated VOT and then the unaspirated VOT, and then I'm going to specify, excuse me, that I'm running this paired samples test by saying paired equals true, or capital T. I'm still going to run it with that alternative equals greater option, but I'm going to get the same result for both, right? This is exactly the same. Everything in these two outputs of the test. This paired t-test is ultimately just a one sample t-test, where I subtract one set of data from the other. And I can do that in this case because these sets of data are exactly the same except for one variable between each sample, right? So just to reiterate that, the paired samples approach only works if your two samples differ in one particular way. Like these are Amy's stops and these are Bobby's stops, or these are the unaspirated stops and these are the aspirated stops, but everything else is the same, right? Or, these speakers are from St. Louis and these speakers are from Chicago, whatever. So in our example test, we were able to match up unaspirated and aspirated stops while keeping everything else the same. So place of articulation, speaker, vowel, context, etc. I'm not going to say that again because I think I've said it enough. And the other part of this that I want you to know is how to report the results of a test like this. I'm going to give you the way I've seen often in stats literature, and which you will probably see as well. this is one of these things. It's a convention, like it's formatting, so it's annoying because it changes over time. And yeah, I'm a little autistic about that. I hate things that change when they don't need to change, but they will. I'm just going to tell you the way it works right now, mostly, so you can do it yourself. But basically what you say is you have the result of your t-test. You report it by saying t, and then in brackets after the t, you put the number of degrees of freedom. And then that t value equals the t-score. So in the example we just had here, t with 209 degrees of freedom, our t-score is 19.4. And then after that, you put a semicolon and then p equals whatever the p-value is. And this p-value is super small. And if you want to report it like this as less than 2.2 times 10 to the negative 16th, that's okay. But usually when it gets super small, people just kind of like stop wanting to like count the zeros and they put p is less than 0.001. And another way I've seen this reported as well, which is valid and fair, is to just say it's less than 0.05. Let's say you're setting your alpha criterion to be 0.05, and if you find that p is less than that, it doesn't really matter how much less it is than that. You got a significant result, right? So you can report it that way if you want to. I like to know the details a little bit, so it's good to know kind of what the p-value is on either side often. For one of our non-significant results, you can get something that looks like this. So this is a t-score of 1.18 with the same degrees of freedom, and the p-value is just 0.24. This is for that first two-sided test we ran up here. Yeah, so, and if you want, you could say it's, greater than 0.05 as well, because that's kind of the crucial part that matters. You could say something like this, oops. And then you'd know it's not a significant result. I keep losing a syllable there. This information is good to know, though. It kind of relates it to like a z-score, right? So we kind of have an interpretation, hopefully intuitive interpretation of what that means based on how big it is. So this is like a z-score of 19.4, which is huge, right? 1.18, though, that's a little more ambiguous, right? We're not convincingly far away from the mean of the hypothesized mean of the distribution when our sort of t-score is that value. So report this as it is. Don't kind of gloss over it like this. But the p-value, people often focus on that because that, basically determines what the result of your test is. But it's kind of less informative than what the t-score is specifically. And you also want to know what the degrees of freedom are too, because that tells you a little bit about like how many subjects you run, how much data you collected, what the shape of your t-distribution is, all that sort of good stuff. I'm going to stop talking now because I cannot talk successfully anymore. See, just did it again. And I've talked long enough anyways. But this is how you basically run a t-test, a one-sample t-test or a paired samples t-test. Next time, we're going to talk about how to run two-sample t-tests, which are much more common in the world of linguistics anyways. So stay tuned for that. It'll be a good one. And I'm going to sign off for now, at last, finished with this lecture set. Till next time.